Mr. Rainsberg here to finish you off with lesson 10.2, which is dealing with significance tests for comparing two means, mu1 minus mu2. The yellow objectives off to the side are the ones that Mr. Ray Nichols covered in the first video for creating confidence intervals for the difference of two means. We're going to be focusing on the green objectives highlighted in the bottom, which is constructing and performing a significance test for the difference of two means and interpreting the results. But before we do that, let's look at something we've looked at since the beginning of chapter 7, which is the inference diagram. And it's important for us to realize when you are given a prompt, read the prompt, determine your population of interest. Do you know the shape? Do you know the center? Do you know the spread? You know, what type of variable is it? Is it quantitative or categorical? Because if it's categorical, you'll be looking at what we did in lesson 10.1. If it's quantitative, okay, well, you're dealing with means. So you have to ask yourself, do you know sigma, the population standard deviation? Is it given to you in the prompt, or was it not given to you? Is it unknown? And because if it's unknown, you're going to be dealing with a two-sample t. If it was known, you'd be dealing with a two-sample z. So this diagram, we're getting toward the end of it, where you need to go through each problem following this process. Before we move on to the actual notes, let's look at a few blue slides to help us understand the procedures that we'll be using. So the blue slides outline the four-step process: state, plan, do, conclude. And it's meant for us to kind of take a moment and determine what we're trying to figure out. And we're trying to figure out, is there an actual difference in the parameters, mu1 minus mu2? Or is everything we found due to chance variation? So when you're dealing with this for the state, remember, you do your null, you do your alternative, you do your significance level, and you define your variables. The null hypothesis is that there is no difference. That's what the hypothesized value is going to be. So we like to say mu1 equals mu2 for the null hypothesis. The alternative hypothesis sets a direction or talks about being two-tailed. Now, we like to use the idea that mu1 is greater than mu2 for the alternative, or mu1 is less than mu2, or is not equal to mu2. You can see in the orange box another way of representing them. That's really your state. And don't forget your significance level. If it's not told to you, 0.05. And you look at random, normal, and independent conditions. So there's the plan step. You have to say what test you're going to be doing. You know, maybe a two-sample t-test for the difference of means, mu1 minus mu2. Well, what are the conditions that we have to check in order to proceed with a t distribution? And that's what we need to keep in mind as we go through the video. We have to remember, how is t different than z? And then we have the do step. The do step uses the formula, test statistic equals statistic minus parameter over standard deviation of the statistic. Now in this case, our statistic is the difference in the sample means. X bars of 1 minus X bars of 2. The parameter is the mu1 minus mu2, the actual difference based off the claim. Well, our claim was that there was no difference, so we could say it's 0. And then you have the standard deviation of the statistic formula. For both of them, you can see it's s of 1 squared over n1, and then you're going to add s of 2 squared over n2. That's the do step. You get a test statistic. You're going to, of course, you're going to graph a distribution, and you're going to shade in the proper direction. And then you're going to figure out, okay, what about my p-value? How do I figure it out? Well, in order to calculate your p-value for a t-distribution, you need degrees of freedom. Oh, man, there's two samples. Well, in this case, keep in mind that that's going to be your issue to figure out is, what do I do if I have two samples? Because the degrees of freedom is usually n minus 1, but I have two sample sizes. Well, there's two ways of doing it. You can use the conservative approach, which says use the smaller of the two degrees of freedom. Since degrees of freedom is represented by n minus 1, sample size minus 1, you don't want to, if you have a sample size of 50 and a sample size of 20, you're going to use the smaller one, because if you say you have a larger degrees of freedom, you're saying you have a larger sample size than you really do. So yeah, you have 50 here, but you have 20 here. So you can't say, let's just use degrees of freedom of 49, because that's going to overcompensate with this group. So the conservative approach is to use the smaller of the degrees of freedom between your two samples. Or you can use technology with your calculator, which will calculate the true degrees of freedom. And it doesn't matter which one you do. So make sure you state to the grader which one you are using. That is important on you to do so they understand how you have your degrees of freedom. And then you have the conclude. You look at the p-value and determine, okay, do I reject or fail to reject? So here's some more information on your plan step, because this is where the meat of your writing, a lot of your writing is going to be. If the conditions are met, you're going to proceed with, you get to name the test, a two-sample t-test for the difference between two means, mu1 minus mu2. Random, well, you have to make sure both of them are random, so you have to check both. For normal, now means, you want to say those are nice because, man, if your sample size is greater than or equal to 30 for both, you want to make sure you can say, yes, central limit theorem is good. We can proceed with T procedure calculations. Well, what if it's less than 30? That's when we really had to use those graphs. And we looked at, if it's between 15 and 30, what do you do? If it's less than 15, what do you do? But if we're going to look at graphs, how many graphs do you have to draw on your answers then? And so we're going to look at that as well. And then independent is the idea of between and within. So keep that in mind. Between, the two samples have to be independent with each other. And then within, usually if it's a sample, that's the 10% condition. But what is it for an experiment again? How do we say it in that case? So remember, we have to determine is it an experiment or is it a sample, because that changes how we phrase our independence. Wow, that was a lot of information on those blue slides. So let's just take a moment and recap, because again, that's meant to just get our minds going on all the stuff that we're familiar with, and then we go into how to do it with the new stuff. So remember your formula sheet, we've already discussed this, but your statistic is the difference in the sample means, x bar sub 1 minus x bar sub 2. The parameter is that there is no difference, so we're probably going to use 0 for that. And then you have to calculate the standard deviation of the statistic, which we have a formula for. And so if we have this, you have suppose random, normal, and independent conditions are met, and we're going to go through an example of those. We talked about those in the blue slides. Then you can proceed with a significance test, and you have to go through and state your null, state your alternative, again, go through that. And look, there's the same idea for the test statistic, for finding t. And then you're going to use that t, and you're going to have to figure out the p-value. But to do that, what does it say? Well, you're going to have to calculate your degrees of freedom, which is your sample size for the first group, n sub 1 minus 1. And then you look at the sample size of the second group, n sub 2 minus 1. And you can use the more conservative approach of the smaller of the 2 degrees of freedom, or you can use technology for it. And that's the stuff we talked about in the blue. And even then, think about what you already know about significance tests. So you have this idea of it's one-tailed. And so one-tailed, you have a mu sub 1 minus mu sub 2 is greater than your hypothesized value. And like I said, usually we're going to use 0 for our hypothesized value, that there is no difference. And you can see where your t is. But one thing I do want to draw attention to is the middle of the distribution is that they are equal to each other, that the difference is 0. And so for our alternative, I have mu1 is greater than mu2. This is the way we've been writing it in class. And what if it's left-tailed? Well, you can see the p-value there is going to be on the left side. And there's no difference for the null hypothesis. So we say it equals 0. For the alternative, we'll say mu1 is less than mu2. So we have these differently. We say mu1 equals mu2 for the null and mu1 less than mu2. So I'm trying to make it relatable to what we've been doing in class. And then you have the two-tailed. Now be careful with the two-tailed, because if you're using table B and you're dealing with a two-tailed, it's only going to give you one side of that, and you're going to have to double it to get the true p-value. If you're using technology, it will calculate the p-value automatically for a two-tailed. So remember, table B is only going to give you the one side for the p-value. You have to double it. For your calculator, it's going to do it for you. And so you have not equal to for a two-tailed, which not equal to. What is that also related to? The video Mr. Nichols did, the idea of confidence intervals for the difference of two means. Remember, you have a significance test that is two-tailed. It is relatable to confidence intervals for the difference of two means as well. Let's get started by looking at an example for calcium and blood pressure. And we're asked the question, does increasing the amount of calcium in our diet reduce blood pressure? Now, a couple things. First, with that question, you see I have it highlighted because that question itself tells you that you need to be dealing with a significance test because you're looking for evidence. Does increasing the amount of calcium in our diet reduce the blood pressure? So you're looking for evidence or something, and that's a significance test. So that question itself tells you to do a significance test. They're not always going to say, perform a significance test. You might have to just read the prompt and determine it yourself. So let's read the rest of it. It says, examination of a large sample of people revealed a relationship between calcium intake and blood pressure. The relationship was strongest among black men. Such observational studies do not establish causation. You know what? I gotta stop. That right there. Observational studies do not establish causation. That sounds familiar. That's a good sentence. So since they, observational studies do not establish causation, well, what did they have to do? They had to do an experiment. Not just an experiment. They did a randomized comparative experiment. There's chapter 4. So we can't establish causation with observations, but we can with experiments. That does sound like something we learned. The subjects were 21 healthy black men who volunteered. Oh man, they volunteered to take part in the experiment. Wait for it though. They were randomly assigned to 2 groups. So good, the random condition was met. 10 of the men received a calcium supplement for 12 weeks, and 11 of the men received a placebo pill that looked identical, so they couldn't tell. The experiment was double-blind. The response variable is the decrease in top number blood pressure for subject 12 weeks, which is measured in millimeters of mercury, of course. We all know that. You see the bold and the underline, and I would start an increase in systolic blood pressure. It appears as a negative response in our results here. You want to test for a positive response. Here are the data. Now, notice we have them bold and underlined for you. If this were given to you on the AP exam, they would not bold, they would not underline, they would not go warning, warning, warning. You need to be careful with your reading. And I also say that because you see up here, I have highlighted the word reduce in a different color. So when I'm reading this, my mind right away at that question goes reduce. My brain starts to think less than, reduce, less than, and then I keep reading down, and I might slip and I might make a mistake because this is telling me, hey, you want to test for a positive response. So there's a little trick right there, as the first part of the question says, hey, does it reduce? But then it says you're looking for a positive response, which positive response makes me think that for our null hypothesis, and our alternative, for the alternative, we're probably thinking greater than. Now you can see here how it's written. Again, I'll write it the way we do in class. We say mu1 equals mu2. In this case, we would say mu1 is greater than mu2. So pay attention there. Also, I would get your calculator ready, and I would pause the video, and I would input in L1, group 1, which is receiving the calcium, and then group 2, which is receiving the placebo. I would put those in your calculators under L1 and L2. Yes, you see a graph here, but there's some things you need to be careful with putting both of them in your graph, because you're going to have to justify here, because I can tell you right now, my sample size for group 1 is 10, my sample size for group 2 is 11. I can't use the central limit theorem here, so I got to do something else. Now, if we use mu1 and mu2, yes, we have them right now what mu1 equals and what mu2 equals, but there is one other thing here I want to draw attention to is, you can see in this, when they're defining their variables, they are not telling you which order they're dealing with the subtraction, which they're supposed to, right? I know, but they did. When they stated their hypotheses, the null and the alternative, they specified the order, mu1 minus mu2. That right there was them specifying the order. Since if we're doing it this way, we would have to define, okay, we're going to be dealing with mu1 minus mu2, the true difference in the mean decrease in systolic blood pressure. So be aware, we would have to define the way that we are performing our subtraction. And also, mu1 is not the average systolic blood pressure. Mu1 is the true mean decrease in systolic blood pressure for a healthy black man. So like the person doesn't have a systolic blood pressure of 7 or -1. That would be really bad. It's the true mean difference that we're looking at. And we have to state our significance level as well, which in this case is 0.05. So there's our state. Now the plan's going to involve some more work. The plan's going to have a lot of stuff. It's because you're dealing with grabbing samples from 2 populations, or in this case, looking at an experiment with 2 groups. Well, if the conditions are met, well, let's see, they didn't tell me my population standard deviation. I'm dealing with quantitative variables, which means means, so I'm probably going to be dealing with a 2-sample t-test for the difference mu1 minus mu2. Random. Well, this is nice. You can't say, oh, it said that they randomly selected. No, they did not randomly select, because this was an experiment. They randomly assigned. Words are important. And so this one says the 21 subjects were randomly assigned to the 2 treatment groups. Well, let's check our normality to see if it's okay to proceed with T procedures. Well, our sample sizes are small, 10, 11, so we need to examine the data. Now, you can see down here that we have the data already graphed for you. But like I said, hopefully you put this information in your calculator, because I'm about to pull it up and we're going to take a look at it. What happens when we look at the calculator? And so if I go right here, I have all my information inputted in my L1 and L2 already. And what I want to do is I want to turn on my plot 1. So remember, second y equals. I have plot 1 already turned on. And so I'm going to show you what that looks like. So I have plot 1 turned on. I'm using list 1 right here as well. And I chose, first off, box plot showing outliers. So that is turned on. Now what I'm going to do is I'm going to hit the up arrow, and I'm going to go to the right on plot 2 and hit enter. Plot 2 is turned on. That's good. So I turned on plot 2, and it also, I have selected box plot with outliers, because who would use the other one? And then I'm looking at L2 for my list. So I have to change this to second number 2 in order to tell it, hey, use the second list. And then I'm going to do zoom 9, and I can see that I have my 2 box plots there. And so that's how you look at it. And what's nice about the box plots with your calculator, it's going to put them stacked on top of each other. Do remember though, when you're graphing, because you can't see this on your notes, is yeah, it does have a scale on the bottom, but it is nice to hit the trace button and write down what the 5-number summary is for each one. Oh man, how do I go to the next one? Well, I think it's below. Yes, I hit the down arrow. Sweet, below, down arrow. It's like it's logic. Then I can choose the other ones here. And so keep that in mind that you can use that. Now you could also, I go second stat plot. I can go here, and I can choose a normal probability plot. So I go all the way over here at the last one, normal probability. And then I'm going to hit the up arrow and do the same thing for plot 2. Now with a colored calculator, while I'm doing this, it's really easy to see the difference in them. I mean, if I hit zoom stat here, I have the red and I have the blue. But if you don't have a colored calculator, you're going to have to do them separate from each other so you can see if there is. Now, there's a little bit of curvature in the blue I see, but not much in the red. The red looks, roughly linear, so that's good news. So I'm going to have to figure out what to do with that blue. So we have that information. That's how you use the calculator. So let's keep going with the notes. And so we have our graphs. Now, when you're graphing it, you could stack the box plot. And again, I would label what your 5-number summary is. For the normal probability plot, you can see we had to graph them and label which one's which differently. And we already addressed that the box plots show that there is approximately symmetrical, no outliers. You may look at it and go, Mr. Rainsberg, relook at your box plots there. I don't want to pull them up again here, but one of them, it doesn't look approximately symmetrical. It's off a little bit. And it's that one right here. And you know what? I kind of agree with that bottom one. But isn't that bottom one the one that also had a sample size of 11? So with a sample size of 11, if you have a 5-number summary, do you see a smaller sample size is going to look in that middle part? That median is going to be looks like it's going to be pulled to Q1 or Q3, but it's because you have a small sample size. It is roughly symmetric if you look at the outside part, the tail parts. Now, the normal probability plot of the placebo, that looks roughly linear. But if you look at the one with the calcium group, the normal probability of that one, there does seem to be slight curvature. But since there's no outliers and there's no clear skewness, we can proceed cautiously with RT procedures. And now independence. When we're looking at independence, it's an experiment. So that means we can't use the 10% condition. The 2 groups were randomly assigned. That in itself, because there's 2 groups are randomly assigned, we can view them as being independent. Now, within the groups, each group also is independent because knowing one subject's change in blood pressure is not going to impact or give information about another subject's change in blood pressure. It's double blind as well, but primarily, if you know my systolic blood pressure, it's not going to impact your own systolic blood pressure. So there is independent between and there is independent within. But, I mean, take a look and pause and read through this because there is a lot of information in this plan step. Just like when we did it for proportions, this is where a lot of your writing is going to be. And especially with T's, when it's less than 30, this is where you're going to have to do some graphing. You got to show graphs for both data. So this is where a lot of it is. So this is where a lot of the time is. But once we get to the do step, the next one, it's not going to be too bad. Again, here's what the calculator can look like. By the way, another reason why you want to put it in there is you want to figure out your x bars of 1, your x bars of 2, your s of 1, your s of 2, because you need those for the test statistic formula. Now, if I look at that, remember, you have s of x and you have sigma of x. This is dealing with a sample, so I bet you we're going to use the 8.74 number and the 5.900 number in our test statistic. So we have it there. Since conditions are met, we can proceed. Good news. Well, that is going to be our x bars of 1 minus our x bars of 2 found from the calculator there. And then we have our standard deviation. Let's see, was I right? 8.743, the 5.90. Yes, so we have our standard deviation squared for each one over the sample size, add them, and then square root. that's going to give you a t statistic of 1.604. Well, if you're using table B, which we are in this case, I'll show you the technology though, don't worry. Well, in that case, which degrees of freedom am I dealing with? I have a sample size of 11, I have a sample size of 10, so that's the degrees of freedom of 10 and 9 respectively, so I have to be conservative. I'm going to use the 9. And so we can see that the 9 falls between 0.05 and 0.10 for the p-value. Do you think maybe on a multiple choice question they might try and trick you with something involving the other degrees of freedom, not being conservative? That's just me thinking out here on how to come up with tricky multiple choice responses. So our p-value based off of table B is between 0.05 and 0.10 using a degrees of freedom of 9. Remember, each t distribution's shape, its curvature, is different based off the degrees of freedom. You have to state it. So you're going to use the more conservative, or you're going to use technology. I wonder what that looks like. Let's pull up the calculator. Stat, go over to tests. Look at that, a 2 sample. Now, am I dealing with a Z or am I dealing with a T? Well, you should know T based off of the notes, but you're dealing with T because you do not know the population standard deviation. So I'm going to hit enter. Now in this case, I'm going to base everything off of the data because we have it inputted in L1, we have it inputted in L2. Do not change the frequency, and we're looking for it being greater. This pooled, no. Just say no to pool. Just say no. Don't do it. And then I'm going to hit calculate. Now, if I hit calculate, it's going to give me everything as well. It gives me my p-value, 0.064, which, by the way, is between 0.05 and 0.10. It gives me my x bar 1, my x bar 2. Good news. It also gives me my degrees of freedom, 15.59051297. Wow, that's pretty specific. So if I'm going to use the technology, I would have to specify that as well. I would have to say, you know what, my p-value is 0.064. with degrees of freedom of 15.6. You got that from my technology of the calculator. Well, in both cases, the p-value is greater than our significance level of 0.05, which means, well, it's greater. That means it's closer to the center. And what's in the center? And of course, I would label my center here being mu1 equals mu2, 0. It's closer there, which means it's getting to the point where, you know what? I think I'm going to fail to reject the null because my p-value is greater than my alpha level, which means I do not have enough evidence to conclude the alternative. And I'll go up to that part, and our alternative is that it is greater than for the differences. So what does that mean? Well, if the difference is greater than, we can say there's not convincing evidence at the 5% level that the calcium reduces blood pressure. So we cannot conclude that. So the evidence is not convincing enough that at the 5% level of significance to conclude that calcium reduces the blood pressure more than a placebo. So this is our state, plan, do, and conclude for an example that was an experiment. And remember, that plan step, that was a lot of writing there. That's where a lot of your information is going to be. That's going to take the most time. So I already showed you all the calculator information. You can also see it right here as well. If I go down, you can see the setup there. You can see the degrees of freedom. But let's go a little bit further. If you think about a state, plan, do, conclude on an AP for response, that's going to be a part A. A part B is going to ask you to go a little bit further with those results. And so this chapter, we've been trying to cover that with you, is relating back to some things you learned before, or even going forward with, hey, what else can I do with these results? So given the results that we failed to reject the null, that we cannot conclude that calcium supplements reduce blood pressure, what type of error could we have made? Well, if I fail to reject the null, that would be a type 2 error possibility in the future. Well, what does that mean in context? Now, we're not asking for a consequence there. The consequence is in part B. We're just asking for context of what it means. Well, in this case, concluding that there is not enough evidence to confirm that calcium reduces systolic blood pressure more than placebo, but it really does. So you fail to reject the null, you have the possibility of committing a type 2 error. So you could conclude that there is not enough evidence that say that calcium supplements reduce systolic blood pressure, but there really is. Now, what's a potential consequence of that? Well, that means, hey, if calcium supplements do reduce blood pressure, we could be missing out on an effective treatment to help reduce blood pressure for people. So that's a potential consequence of that type 2 error. Now, what would happen, and these are always good problems for multiple choice too, is what would happen if you change your significance level to 0.10 instead of 0.05? Now, if we remember, I think it was around like a p-value was around 0.064. Well, in that case, that p-value is smaller than our alpha level. And in that case, you know what happened? That would change our results. That would change the results. That would change our conclusion because our p-value is less than 0.10, which means we would then be able to reject the null. And we would be able to conclude that there is convincing evidence that calcium supplements can reduce the systolic blood pressure more than a placebo. So when you change your significance level, there's a possibility that you could change your results. Again, pushing what you discovered in the state plan to conclude one step further, and that's where type B and free response questions come into play. All right, so how does it relate to what Mr. Nichols covered in the first video? How does it relate to confidence intervals? So one thing to keep in mind is a confidence interval really relates to two-tailed significance tests. However, what we were dealing with in this example is we were dealing with a one-tailed significance test. We were dealing with information over here, and we had alpha of 0.05. Well, if I wanted to create a confidence interval, I'm going to have to figure out, well, how can I make it relate? Well, I don't want to, and I can't say, you know what, I'm going to change that alpha level on this tail, because then that's changing my results in the test. I have to keep this same alpha level. So if I want to make this a confidence interval, and I want to keep that same alpha level on the right side, well, I have to make it two-tailed. Well, if I make it two-tailed, it has to be symmetrical, which means I'm going to put an alpha level of 0.05 here as well. So we have our information. So what is this? What confidence level am I really dealing with? I'm dealing with a 90% confidence level. So that's what this is really, the first part is trying to tell you. We can estimate the difference of the true mean decrease in the systolic blood pressure for the calcium and placebo treatments using a 2-sample t interval for mu1 minus mu2. Look at that. It is defining using a 2-sample t interval. But to get those results, you have to be consistent. And that's what I was talking about with the one-tailed test. And our one tail had a 0.05 on their right side. So to be consistent, I cannot change that right side. So I have to create a left side which is equal to it. That really makes me have a 90% confidence interval, with my degrees of freedom in this case still being 9, the more conservative of them. Well, for 90%, you have a t-star of 1.833, and you can plug it in. Remember this part, you have this being your margin of error, 6.027, and what you get is negative 0.754, comma, 11.300. That's going to be the confidence interval that relates to it. Now, in that interval, 0 is contained. Remember, 0 means there is no difference. It relates to the null hypothesis, the claim that there is no difference. Well, 0 falls inside of that interval. Our interval captures 0. It captures the difference in the true mean blood pressure. So, because 90% confidence interval includes 0 as a plausible, not possible, a plausible value for the difference, we fail to reject the null. So this also relates what we're going through at the 10% level for a two-sided alternative, or at the 5% level for a one-sided. We fail to reject when 0 is captured by the confidence interval. Because 0 is the claim that there is no difference. If you capture it, then you fail to reject the null. If 0 is not captured, you state it's not captured, but then you have to state in relationship. Is it above? Is the interval above 0 or below 0? You have to state direction if it's not captured. And so we have our calculator as well. Mr. Nichols went through how to use it to construct a 2-sample t interval. We can do it with our data as well, set up there, and you can look at it. And so we go through using t procedures wisely. By the way, we've already covered all this previously, and I'm just going to quickly go over it. You need to make sure you realize if n is greater than or equal to 30 for both samples, you can use central limit theorem. If it's between 15 and 30, well, you have to make sure there's no outliers and there's no strong skewness in both of them. If it's less than 15, good news is I really don't have to go into detail there because we did an example of less than 15. No skewness, no outliers, check the data. And all of these, make sure you graph these. These conditions for using t procedures safely has not changed since the first time we have used them. They are robust, but they're robust with certain characteristics. There's certain things they must meet to be robust. And so last but not least, if you're using them wisely, a few precautions and considerations to keep in mind when using two sample t procedures is when planning a two sample study, try to choose equal sample sizes if you can. It's not always possible. You saw the one where we had an experiment of 21 and one group was 10, one group was 11. But you don't want to look at a two sample t procedures test with a sample size of 500 and compare it to a sample size of 20. It's just not good. So try and make them equal sample sizes if you can. And do not use the pooled two sample t procedures. Do not do that. We are using safe procedures we are safe using t procedures for comparing two means in a randomized experiment. This is telling you experiments still play a role for us. And right down here, do not use two sample t procedures on paired data. Remember, know the difference between a paired test and a two sample t test. Paired tests look at really one population, and you're looking at two things on it, a before and after, a treatment 1 and treatment 2. You're looking at one population, and you're trying to see, is there a difference if you do two treatments on that one population, or you look at two drugs on that one population. You look at old Coke versus new Coke for one group. Which one do they prefer? When you're doing a two sample t test, you have two populations. You're taking a sample separate from each one of those. There is a difference, so do be careful and be aware of making inferences in the absence of randomization. Seriously, we should know that by now. Randomization must be present in order for us to infer on a larger population. Now, you have images here of your calculator to show you what to do for each one, for 10.1 for an interval and a test, as well as for 10.2 for an interval. Look at that, don't pool. And for a test, oh, look at that, don't pool. And you have the idea of some things with two sample t inverse procedures, confidence intervals, t tests of significance, degrees of freedom. Remember, there's two options. You can see there's technically three options. We didn't tell you. There is a formula for degrees of freedom. I would rather use the conservative approach or have my calculator do that formula for me. So we don't consider there to be 3. And that's the end of the video. If you have any questions, please pay attention and ask in class. Thank you for watching the video. Please remember to both like and subscribe so you will be notified when new videos are made. And continue to support our sponsors, like this one. Hey, you caught me putting the finishing touches on our new album, Random Inference, Statistically Significant Songs by Mr. Nichols and myself, Mr. Rainsberg. This album includes songs such as You Made a Type 1 Error When You Rejected Me, and Our Love Is Significant, It Did Not Occur by Chance. Now, my personal favorite is Your 3 Standard Deviations Above the Mean. But right now, you have an exclusive opportunity to hear our soon-to-be world-famous song, Pull to You Like a Mean to an Outlier. So watch the video.